This is EGME-331 solid mechanics. In this video, we'll be reviewing bending stress. Now let's take a look at bending of beams. So bending stress is caused when the beams are subject to an external load. As we can see in this figure, the load is applied perpendicular to the axis of the beam, and the beam bends, or we can also term this as flex. So flexure is a term that associates with beam. It's unlike tension, compression, or even twisting. Bending is a different form of stress. It results in the beam becoming a curved shape, call it as a deflection curve or the elastic curve, because the bending stresses are mostly within the elastic limit. Let's try to understand the plane here, because the plane of bending is important. If you could see the XYZ axis over here, the XY plane is the plane on which the beam bends, and the load is applied in the Y direction. The bending or the flexure happens around or about the Z axis. It's basically a rotation about the Z axis. In the past, beams were made of wood, and because of that, the wood was made of fibers. So always the beam concept were associated with longitudinal fibers, and since then the beam started being made of metals and other materials, even composite materials. Nevertheless, the concept of the wooden fibers still is used, at least for the theoretical purpose. So the beams are assumed to be made of those fibers only for the theoretical purpose, which means that if you consider the beam along its axis, you could see so many fibers along the axis of the beam. Let's take the case of pure bending. So what's pure bending? It's as you can see in this figure here, it's a 2-point loaded beam where you could have a constant bending moment on the bottommost figure. The between the points B and C, the bending moment is constant, and the corresponding shear force is 0. Why do we consider pure bending? Is because the beam theory was developed based on pure bending. It is the simplest case of bending where the shear force is 0, and we are deriving the beam theory based on the pure bending scenario. So let's say we take a section of the beam when it is subject to an external load. It tends to flex. So it depends on the direction of application. If the load is applied upward, you could see a shape of an inverted U, and when the load is applied down, you could see a shape of a regular U that you can see in this figure right here. What we are trying to see here is the fibers, as I just mentioned. This is just a theoretical assumption. The woods are not being used for making all the beams, which means the beam doesn't necessarily have fibers, but we consider fibers running along the section of the beam. If you consider a bending scenario, as you can see here in this figure, towards the top side, or top, I won't say the half, but towards the upper side of the section, the fibers tends to contract, which means its length decreases. On the other hand, on the bottom side of this section, the fibers tends to expand. That means its length increases. Naturally, there would be a fiber between the contraction and expansion which does not change its length, which means it's not subject to an expansion or contraction. In other words, you could say it's not subject to any force. And this particular fiber, it's actually a plane, because this what you're seeing is a 2D figure, but in reality there's a thickness. That means we are talking about a plane. We call this particular plane as a neutral surface, and the axis that runs through the middle of that plane is what we call as the neutral axis. Why is it significant? Because at neutral axis, the forces acting are 0. Above that, there is a compression in this particular case, and below that, there is a tension. The neutral axis or neutral surface is used to determine the bending stress that acts on the cross-sectional surface of the beams. Now the neutral axis, as I mentioned, would have two parts, right? It's not necessarily half or the middle, but it could be an upper side and lower side. Let's term it as an upper side and the bottom side. The scenario that we have considered, the upper side would have compression and the bottom side would have tension. If you see the cross section, this is a sectional view, the perpendicular view from the previous figure. The top portion of the beam is subject to compression. The bottom portion is subject to tension, and we have the neutral axis right there. At each point, if you consider on this cross section, the intensity of the force as well as the stress changes because it is having a certain distance of y away from the neutral axis. So depending on the location that we are talking about, there would be a different stress. That means the stresses acting on the surface, the cross section of the beam, are not uniform. It is linear or linearly varying away from the neutral axis. For our better understanding, the neutral axis of a beam passes through its centroid of the cross-sectional area. That means if you take each section has a centroid, and if you connect all the centroids together, that line would be the neutral axis. Here we can see the variation in the stresses. So the stresses, they are normal stresses. The upper side is shown inward, that's a compression or compressive stress, and the bottom side is expanding, that's a tensile stress. What we could see here is at the neutral axis, the stress is equal to 0, and away from the neutral axis, that means it increases away from the neutral axis. That means the highest point of the stresses, the compression, would be on the top surface on in this particular case, and for the tension, the highest point would be on the bottommost surface, right? So if you are able to design a structure based on the highest stress, that's what we always do for any designs based on stress calculations. We try to find the highest number, and in this particular case it would be the extreme surfaces where the stress would be the highest. This stress is what we term as the bending stress, and the bending stress is also termed as flexural stress, because we are talking about like flexure here or bending here, and the equation that we see here is derived, and this is termed as the flexure formula. In this figure we have three terms, m, y, and I sub z, where m is a bending moment that acts about the z-axis, that causes the stress to produce on the surface. Y would be the distance away from the neutral axis, the point that we consider its distance away from the neutral surface, and I would be the moment of inertia, or I sub z is a moment of inertia. If you notice the flexure formula, you could have seen the negative sign. It's important to understand the sign convention as far as bending stress is concerned. So a positive bending stress, or a bending moment, a positive internal bending moment, as you can see in this figure here, is where the compression stress is above the neutral axis. That's what we call as a positive curvature, where the compression or the compressive bending stress is above the neutral axis. So that's what we call as positive. When I say compression is above the neutral axis, the tension would be below the neutral axis. Similarly, for negative bending moments, the compression will be below the neutral axis, tension will be above the neutral axis, and this is the case where we use the negative sign. So the sign convention is important because of the change in direction of the bending moment, up versus down.